Hello, guys. First of all, I would like to say that along with my colleague Kostas, we're very happy to be here today at the European Summit on Data and AI and present to you our personalization journey from single node to cloud streaming. So our aim is to present to you all the bottlenecks and the challenges we faced along this way, and also share with you the way we went forward and what we did to go through this process. So before I get in the technical part, let me first introduce myself. My name is Stefanos Doltsinis, and I'm machine learning architect at Kaizen Gaming. My co-author, my co-speaker and colleague is Kostas Andrikopoulos, and he's a big data architect at Kaizen Gaming as well. But before I get in the technical part, let me first talk to you a little bit about Kaizen, our company. Kaizen is a top game tech company in Greece and one of the fastest growing in Europe. And we currently operate under two brands. We have Stichman for Greece and Cyprus, and Betano, which operates in Romania, Germany, Portugal, and recently in Brazil. And it didn't take us too long to realize that if we want to offer a good product to our customers, we should invest in technology. And our aim is to provide more personalized content and also personalized offers. So what we thought is that we should take down the road of machine learning, and with this in mind, develop some machine learning applications and some machine learning models in order to automate our decision process and provide more personalized content to our customers. But before I get in what we do today, let me share with you a little bit of our history and our initial workflows. What you see on the right-hand side is a number of different components we used to use. We used to have several data sources. We used to have a data warehouse, a lot of databases, files, and so on and so on. And this is a very big challenge if you don't share a single point of truth, a single point of reference. We also used to use our local workstations for training. And this, as you can imagine, if you have a lot of data, also becomes a very big challenge to go through. And finally, in terms of the application, we had the model and we had the application that in order to push that in the production, we had to build an image, a Docker image, that had to go through a process that is complex on its own. So, as you can imagine, with this initial workflow, we had a number of issues, we had a number of challenges, and what I've tried to do in this slide is to break down those two into machine learning and application. And in terms of machine learning, what I want to mention here is three different aspects. I want to focus on data, on our features, but also on our model. And from a data perspective, the first thing we realized that it was going to become an issue was data availability. And what I mean by that is that everything's straightforward. If you want to use 1 week or 2 weeks of data, but everything becomes a very big challenge if you want to train with 1 or 2 years, then this is where your local workstation shows the limitations. Another thing that I want to mention is what we call time traveling. And by time traveling, we mean if you want to get the state of your data at some specific point in time, and you haven't catered for that while you're storing the data, then it's very difficult to fetch. On the feature side, we faced a lot of issues with the recalculation. And what I mean by that is that because you put a lot of effort on calculating your features, if you don't make sure that you calculate them properly and you store them properly, then you will end up in a situation that you will calculate them again and again. And this is essentially all of the processing power you're putting in that, which makes sense to not repeat, and it will cause you issues. Finally, on the modeling, versioning was a very big challenge. It wasn't always that easy to make sure that what is running in production was also what you trained and what you wanted to push to production. So that was about machine learning. I will also go on the application side. I will not go through all of the bullet points. I will mention scalability, which we thought it was very important. And we always need to have in mind that everything comes from your front application. And your application, your machine learning application, should be ready in order to consume the data, scale for this data, and be ready to process any upcoming spikes. So this is where we used to be, and these are some of the challenges we faced, and I'm sure that all of you have faced similar challenges. And this is the point where we decided that we should go forward, we should change our approach, and should go to a big data infrastructure. And towards this direction and this process, my colleague Kostas will talk you through.
So if we take a closer look to the challenges that we're facing back then, you see that there are typical issues related to the life cycle of machine learning projects, where MLflow can be really helpful. Also, we're facing challenges with the velocity and the volume of the data that we needed to process. And by using Databricks on Azure, we not only got the necessary scalability, but also the elasticity that we needed. So if we fast forward where we stand right now, about 6 months later, you'll see that we have hundreds of data pipelines, starting from traditional ETLs, where we extract our data from various data sources and we store them to our data lake. And we are now able to reason about the correctness of our data with the asset guarantees that we have, and also the schema enforcement. And as Stefanos mentioned earlier, this is really important for ML applications to have a single source of truth. So it is easier to start developing your pipelines. So we start from feature generation up to model training and performing predictions. And now, with the use of MLflow, our ML team is able to collaborate more efficiently and to share their findings. Another thing that I would like to highlight at this point is that all this progress wouldn't be possible if we weren't able to reuse part of our code base. And I'm not only referring to the Python code that was part of our ML libraries that was ported into Databricks notebooks, but also our SQL transformations that were part of our data warehouse ETLs that was ported into Spark SQL. So having a proper stack in place is really important. But what's also important is to be able to design your pipelines in a proper way. So having the proper stack is one part of the solution. What's equally important is to be able to have a proper design in your pipelines. So in order to do so, you need to think of what is your input data and what is the optimal output for your data. And you should be able to reason about your choices by thinking of what's the necessary latency that you're trying to achieve and who is going to perform the actions. And when you answer to those questions, the how will become clear. So now we will present you two distinct use cases, and we'll see how the difference in the requirements will affect our design. So we start off with a use case where we use our latest data in order to feed our model and perform predictions. And actually what we're trying to achieve is to feed those predictions directly to the microservices in order to take some responses, to take some actions. So what is that we have is that we start with structured data that are stored in Kafka in Azure format, and we try to keep the latency in the order of a few seconds. And the reason why we want to do so is because there is no human interaction in this pipeline. We want our microservice to be able to perform some actions immediately after the predictions are ready. So the best way to achieve this is to store data into Azure format back into Kafka, where our application can directly consume them. So I believe that by now, how we can able to achieve this is pretty clear. We use structured streaming to perform the feature generation, and we store those predictions back into Kafka, where we have a second structured streaming that reads those generated features and feeds them into our model and store the predictions back into Kafka. And the reason why we're using two structured streaming is that we are able to scale better using this way. So whenever you find yourself that you have an event-driven application where you want to take immediately actions after when your data is available, it makes sense to store your data into Kafka, because not only you are able to achieve low latency, but you also are able to handle issues with slow consumers. So let's see now a more complicated design where we have three major differences. The first one is that now our application is not an event-driven, in the sense that it runs periodically and uses all the available information to perform actions. Another major difference is that now our model is rather complicated. So it uses way more features in order to perform the generation of the output. And also, some of the features not only require recent data, but also historical data. So if we switch back to our what and why questions, we now have not only structured data that are stored in Kafka as we used before, but we also have delta tables that hold the historical data. And what we're actually trying to achieve is to match the latency of our pipeline with the periodicity of our application. So since our application uses all the available information, it makes sense to store our data into a SQL table. And we used PostgreSQL for this one. And also, because we want to keep a history of our predictions, we also are storing the results into a delta table. So how we can achieve this, and what are the challenges that we have? First of all, we use structured streaming to load the recent data and the state in order to perform the feature generation part. And because our features are also taking part into different feature vectors, we want to store them as delta tables to actually use it as our caching layer. The second challenge that we have is that it's not trivial to join hundreds of features together as streams, because there are many limitations when you use structured streaming. So as a second step, we switch to batch processing, and we take all those delta tables and join them together to compute a feature vector. And as a last step, we use, once again, structured streaming to get the latest data of our delta table and feed them into our model to perform the predictions, where we store them back in the PostgreSQL and also in the delta table. And the key takeaways from this design is that whenever you have features that are computationally heavy, it makes sense to store them into delta tables, because actually you have a lot of optimizations that you can perform. Also, whenever you find yourself in a need of joining multiple features, it makes sense to switch to batch processing. And last, if your application doesn't have the limitation of using a SQL database, a Cassandra would be actually a very good fit for this use case. So I believe that by now you have a good understanding of our design. So Stefanos will walk you through the details of our journey, of our personalization journey. So Stefano?
So Kostas talked about a couple of different architectures that we're using on our day-to-day pipelines and for our streaming. But our aim is to offer personalized offers and personalized product to our customers. So with this in mind, we have developed a couple of applications that I'm going to talk to you about now. First of all, we have what we call sportsbook personalization. And before I get in the details of this project, I'll first say a couple of things in order to understand what's the rationale behind it and what we're looking for. In our day-to-day, we have around 3,000 unique games that generate a number of different markets. And on those markets is the final product that appears to our customers. So our customers have to walk themselves through all of this information in order to find what they're looking for. And in several times, this can be very frustrating. So what we thought was that if we can offer a personalized content, which is filtered down to what they're looking for, to what they want to bet on, then we can improve their experience and finally increase their loyalty. And from a technical perspective, we decided to build a recommendation system. And to do that, we went with a collaborative filtering approach. And in every collaborative filtering approach, what you do is you first build the utility matrix, and which has the preference of every customer. In a utility matrix, on one axis, you have all of your customers, and on the other axis, you have all of the potential events which every customer can choose on. And initially, you use the preferences, the historical preferences, to fill in all of those customer event combinations with some kind of ranking. So as you can imagine, this is a very, very sparse matrix, and it's sparse because most of the customers have only chose to play in the past just a few of the potential upcoming events. And in a collaborative filtering approach, what you do is you take the sparse matrix, you move it to a latent space that tries to capture all of the customer game combination dynamics. And once you've done that, you bring it back, and through those dynamics, you try to fill in all of the gaps in the sparse matrix. And those gaps are finally the preferences of your customers. And based on the ranking that you have just generated, you choose to offer to your customers the top-rated games. And in order to do that, we used the Spark Machine Learning Library, and we chose to go with the alternate least squares algorithm. So in a daily basis, we train our algorithm, and what that means is that we fetch around 600 million of transactions because we use 1 year of data, and we produce a utility matrix which is about 400K customers times 300K unique games. And as an end result, we export 500 million daily recommendations. I have to say that we do the daily training because we want to capture the latest preferences of every customer, because every day you have incoming data that you want to incorporate in your final model. A very big challenge that we faced in this project, and I want to highlight, is what we call dynamic content matching, because the upcoming content, in general, our content is very dynamic. So the upcoming content is not necessarily something that we have seen in the past, and we have to find a way in order to match the upcoming events to our history in order to take the most use of our training data, historic data. Finally, at this point, I want to mention the metric we're using to evaluate our project, and this is the mean average precision on the top 100 games, and we're performing in an average of 70%. So that was about the sportsbook personalization, but as I said, we have a couple of applications, and the next one is what we call real-time computation. And the rationale and the motivation behind this project is very, very clear if one thinks the fact that a reward increases loyalty. And I don't think this is debatable if you think that around 40% of our customer communication, our customer support communication, is about some kind of reward and some kind of bonus request from our customers. So this communication ends up in about 4.5 million reward assessments per year. And I'm not sure if this is a big or a large number to you, but I do know that it has two different aspects. From one side, all of those assessments need to be done manually and periodically, which means that we need to have people to do a repetitive task in a very, very large scale. And on the other side, we have our customers that need to wait for this periodic assessment, and most importantly, they will end up with an offer which is not necessarily personalized. And having this in mind, we thought that we should design a system, we should design a project that it will be real-time, and it will provide real-time decisions as a bonus allocation, which a bonus allocation result. So from a technical side, what we did in this project is what you see on the right-hand side of the slide is one of the architectures that Kostas presented earlier. And this architecture fits very, very well to what we've done in this project. We're essentially streaming our data, and we're using those stream data to calculate a number of different features. And essentially, in the end, what we want is to stream our predictions. To do that, we're using a binary classification model. We're using, again, a Spark Machine Learning Library algorithm, a gradient boosting algorithm. And we stream the prediction, which ends up to an allocation of a specific bonus for every one of our customers. But what I want to highlight in this project is the use of MLflow, because we're using a number of its different aspects. We're using experimental tracking, we're using model deployment, but we're also using model registry. And I have to say that I'm really surprised and fascinated with model deployment, because you can have your setup, you can have your training pipeline, you can change whatever you want to change. And then if your model fits well on actually performs well on your validation set, then you can instantly just deploy the model by changing its status to a production model. And this is a very big difference to what we used to have before, where we had to go through a Docker image and push to the production. So as a last thing, I want to say that the model registry has also helped us very, very much, because you can always go back and see how your model used to perform, and you can compare it to your current performance. And this is something that helps you a lot with a monitoring application. So this is where we are today. This is what we've done on those couple of use cases, but this is not where we want to stop. We have a very big vision, and we're aiming for that. And Kostas can talk you through.
So our future steps is to move closer to CAP architecture, where we want to switch from batch processing to real-time processing. Also, we would like to evaluate the use of Cassandra for the use case that Stefanos mentioned before as a replacement of PostgreSQL, but also as a feature store in order to be able to reuse our features. And since our experience with MLflow is really amazing, our next stop is to use model serving, but where it seems to be a perfect fit for various use cases that we have. And last but not least, we want to also use Redis in cases where applications performing single key lookups. So please stay tuned for our next journeys. And at this point, we would like to thank you all for attending this session, and to remind you that your feedback is really important to us. So please don't forget to rate and review the sessions. Thank you.